Hello. Good morning.
Good morning.
How is everybody? Erlinda is awake. Anybody else?
Good. Tired.
Getting there. All right. Did everybody have a chance to take a look at the grading? Yes, no, maybe. Solutions? I was thinking I should probably work through a couple of problems from, well, at least one, the last one, but maybe first one and the last one from the exam. Does that sound like a good plan?
Yes.
All right. And then, what was I about to say? Yeah, so apologies for the delays. I had a technical problem with my computer. This thing just stopped connecting. And the only way was to kind of essentially do some very interesting twists. And at some point, it just like kind of like that was the afternoon, like I could basically hold and type to charge. And then after that, like it just stopped working altogether. So that took a good portion of my Monday evening and Tuesday morning. So that delayed the grading. So apologies for that. But all is well. Got figured out before next teaching. So my laptop is charged. Okay, let me get. I will do a separate one. New. The exam 2 video. All right. Let me open up a PDF, share my screen. And one more. Let me also show the problem. All right. So first problem was on estimating permeability of a sample cubic packing of equal spheres with certain radius and the packing porosity 47.6%. And by two methods. One is Kozeny-Kármán's formula, which is a given formula that we mentioned in class. And tortuosity is basically geometric tortuosity of the tubes going across. In reality, it's a fitting parameter when you have experimental measurements and you have estimate of the grain size and you have measurement of porosity, for instance, helium porosity measurement, then this gives you essentially, and you can measure kappa, so that gives you a way to adjust the formula to work better when you're trying to fit things to the permeability. Now, this is a formula that was derived. We didn't go through derivation, but it is derived for disordered packing of spheres of equal radius r, and phi is the porosity. So in this case, it was really just about fitting the numbers in, and one had to basically estimate something about the porosity. So essentially, since I had let me do a snapshot. So this is the packing, and packing is regular. So if I'm looking at the major paths going from here to the other side of the packing, it's kind of straight. So essentially, as far as we can see in these packing, there is no really tortuosity or not a major influence of it. This is not to say that some of the flow will not go down and be more tortuous, but the main flow paths are straight. So I essentially wanted you to kind of exercise estimating things when you don't know them, which is pretty common in porous media, and say, okay, this should be a porosity 1. So just to then write that down. So this is so B is 0.476. R is not specifically given, so it can be just left as a parameter in there R that you plug in, or you can assume one. That was fine as well, either way. So from the arrangement, tau is approximately 1 to have straight tubes. So then I'm going to assume that K is the cube, 18 tau, 1 minus T squared, R squared. And you plug in those numbers, so this is 0.76 over 18 times 1 times, I think it's 0.524 squared, R squared, you get about 0.0218 R squared. Okay. So this in itself, bundle, Karman-Kozeny model is not the same as bundle of tubes model. Bundle of tubes model assumes that those tubes are straight. So essential difference, specifically in how Logan, looks like I got kicked out of the Zoom meeting, but I'm back. Is it just me or did everybody else see anything?
I think it was just you.
Okay, I feel special now. All right, well then, let's connect back. And it took a moment. It was kind of it took a moment to find the network again or something. All right, back to this problem. So this was relatively straightforward, just applying the formula. The only catch that you might have not been so comfortable with is estimating tortuosity. In general, tortuosity is larger than 1. So I'm gonna, if I'm going across a porous medium, I'm going to take a longer path than I would if I just went, if there was no porous medium and I just went straight down. All right, now the second portion of it was the tricky part. And it said, okay, in that packing of spheres, and I'm gonna redraw, estimate this using a bundle of tubes model. And the biggest question was, well, which type of a tube? So if I look at the cross section, which was provided for you, the main pore or pore throat going across, I can never somehow draw the same circles. Okay, so these are
Dr. Pradanovic, you're not sharing your screen.
Okay, coming back into Zoom. I forgot to do that. Zoom. All right. Okay. So basically, when I look at this, let me just show this on the sketch that looks nice. So if I have, so question is, I have this tightest portion in between 4 spheres. And this is my major constriction that is basically constricting or influencing the flow. And I can assume in bundle of tubes model that this is a cross section that is going across and is the same. So now I need to somehow fit something more realistic in there. I am having all kinds of issues today. So in this problem, I have to go. I am in the middle of teaching, I apologize. Yes, I got it. It's fine. Okay, yes, okay. Talk about a day today. So if we have a cross section of a pore throat, I'm trying to fit a realistic cross section, and I'm assuming a bundle of these going across. I can see this sort of repeats. So this is I really need to, since it all repeats, I need it really to focus on this one. And this kind of a thing just repeats for all of the cross sections. So if I'm looking at the permeability, all I really need to look at is permeability of this particular portion. Excellent. So now what? I could fit in a circle in there. And a lot of you actually assumed a bundle of circular tubes, but you assumed the radius of that tube to be r. Well, r is radius of the sphere, so that's not what fits into this. This is way smaller. So you can estimate what this radius are, so that would be option 1. And there's again multiple options, all are approximate, so it's not that there is a perfect solution. But one option would be, oops. Okay. Oh, come on. So one option would be something like this, but this radius you would get from here, okay? So essentially, what is the distance between these two? And this is our, and so is this, if I could actually draw straight lines. So that's one option. So there is a tube or radius, I'm going to call it R, okay? So there is a tube of radius, a tube cylindrical of radius R could be inscribed. I'm going to argue that another option, and that's the one that I chose in the solution, but you have to find, you need to find R. Okay, from this geometry. Another option would be simply to say, okay, well, this is sort of like a square. And I can figure out what is the side of the square. So that's option A. Option B would be, okay, a square tube. A square tube. And side is A. And that's the one I opted to. One could also, that there's a third option here, actually inscribe a square. And I'd argue that that would fit a little better than that. Okay, there's two possibilities. All are approximate. So the one that I did in red, that one slightly overestimates because the actual throat is a little tighter than it, that one. So that one will slightly overestimate permeability. And inscribed circle or that inscribed square, right, would slightly underestimate. And you have to be comfortable with that. Actually, a good idea is probably in general to try to consider both and see what is the possible range. Okay, because you are making an error and you have to be comfortable making an error. But I'm going to proceed with this red one. So that's on the outside. So then the side R, so we have R here, R here. So basically my R is, A is square root of R squared plus R squared. So it's R square root of 2. Okay. So that is my side length of the square. After that, so I know that I can do estimate volumetric flux through a square. That's from lecture slides. And volumetric flux through a square is given by approximately 0.351 a to the 4 delta p over mu L. So this is 411 tube with square cross section. Okay. And now permeability of N of them, and really we are looking at only one because that's the representative, but I'm looking at this cross section that I outlined here. So my Q total divided by area would be number of these tubes. I'm just gonna keep the notation from derivation in class times this square cross section volumetric flux divided by A. And that has to be compared to Darcy's law, K over mu delta P over L. So this is comparison of bundle of square tubes to Darcy's law. And that's essentially how I back out what my permeability K is, okay? And we did that in class for cylindrical, and I think I did an example for triangular throats, so the procedure is similar. In this case, A is basically the total area of the cross section that I'm considering. Now, if this, in general, how do I relate this to porosity of the tube? So I know that my number of tubes times the area of the square tube divided by the overall area that I'm looking at, that's basically what's considered a porosity of the cross section, and I would relate that to the outside measurements. In general, if I was doing bundle of tubes for a general piece of rock, I don't know how many of these tubes do I have across, and basically, but I basically relate number times assumed cross section divided by the area to the measured porosity. Here we have a measured porosity, and we could do that. I could also just say, well, I am looking at the representative area that just repeats. So I could also, so normally take measurement for it. What I'm going to do is I'm going to say, well, I know everything about this geometry because it's so regular. So I'm going to use to estimate from the geometry that we're looking at, from the given geometry. And what I'm seeing is one tube, okay? The area of the square is a square, and area of the representative part that repeats is actually this one, because that's what's stacking up and tiling up. So up here is already the beginning of the next one and so forth. So my A is actually R square. 2R square, sorry. So that's 4R square. So that's the area of this representative part. And then if I look at the NAS divided by 4, A square is 2R square. So basically my NAS over A, based on this geometry, which is just taking the cross section into account, it's 1/2, which is 0.5, which is pretty close to 0.476 that was given, that is actually estimated from the volume. Okay, so the volume geometry versus cross section geometry. So it's close enough to 0.476, and you can use either. Again, these are approximations, and there is no exact thing, like exact one way to solve this. All right, so what is now my permeability? I now go back to this. So I know what this QS is here. I know what N over A is, so I can basically plug that into, so N over A is 0.5 times ASA square. So I can plug that into here. I have QS. I also have, well, I don't have this, but it's actually, it repeats in QS because all of the tubes are exposed to the same delta P across and the same, they're assumed the same length. I'm using the same fluid with viscosity mu. So basically, this portion that I actually don't know what is the pressure difference that I applied will cancel out. So when I put that in, I will get that K is 1 over delta P over mu L and over A S. And when we plug everything that we know, we get estimates like this. So the other one was about 0.02. This one is about 0.03. Neither of them are right. They're all approximate. And this is common for petrophysical formulas. Again, all of them are some approximations. So there is an error that is in there. They're based on simplifying assumptions and using analytical expressions where available, whereas the porous media that we deal with is not necessarily that regular. Any questions?
Could you go back to the original question? I did have a question about the wording of it.
Okay. This was
The bundle of conduits. So is the bundle of conduits the same as a bundle of tubes?
Yeah. That's
Okay.
English. English problem. English language problem. Yeah.
I've just never heard of
Conduit,
conduits.
tube, channel.
Got you.
Sorry, I did not think that's, yeah. Okay, any other questions? All right. So the second problem, and again, these are posted, the solution key. Have you all found it? In files, there is Exam2, and I dropped the PDF in there. So let me know if you don't see it. So this problem, I think I want to focus more time on the third one. This one is very, and most of you did get it. So this is fairly similar to what we had for homework, and basically example that is following 10.6. So there was an option of, if you derived it, that was great. I appreciated seeing the derivation, but some of you just use the formula from the book. That is fine too, as long as there's a little bit of a twist. And I did catch some of you on it. So this was ever so slightly, this portion here was ever so slightly differently defined compared to what book defines it. So book does not take RI, this inner radius, into UI. So that was just a little bit of a twist. And even if you use the formula, you still had to, the number of layers and so forth is not necessarily exactly matching. So that had to be reconciled. So that's not necessarily all very straightforward. So what do we have? We have inner radius of 2.5 centimeters. So here it is in meters. The tube is here, and then there is an outer radius of 5 centimeters. And essentially water is flowing through this and heating the oil on the outside. Now, oil on the outside has a temperature T or O, and oil on the inside has a temperature TW. And this difference in temperature is driving the flux across these cylinders. Okay? As the time goes by, asphaltenes pile up on the outside. And the question here was a practical one. How are you going to improve the heat transfer, which that's what you want to do if you want to heat things up efficiently. And this scum essentially has, or asphaltenes that have piled up, they provide certain resistance to that heat transfer, and that's why you want to remove them. So question is, if you just remove the scum and everything else staying the same, what is the efficiency of the heat transfer compared to the original? And that's essentially done by comparing these UIs. Okay? And the second question is, if you increase the Newton's law of cooling coefficient, transfer coefficient H0 on the outer surface from 50 to 500, which is basically by increasing turbulence in the flow. We haven't gone through these formulas, but we've done everything analytically for laminar flow, but there are certain coefficients that are called friction factors that basically are put into the solutions to account for turbulent flow. So this is just FYI. We skipped that chapter because we don't, but this semester is an interesting one. So they basically, but I'm just telling you here, okay, this HO increases. So what do we do? Okay, we put in all of these into formulas, and if I use the formula that is in the book, from BSL, that basically looked at the flux and what it is in terms of the temperatures. Book uses A and B, so now A is my water, B is my oil, and RO in the book is my inner radius RI. So what do? I have this transfer term on two different materials, basically fluid to solid, which is where what comes from Newton's law of cooling. And then I have it also on the other end for also Newton's law of cooling between the solid and the fluid again. And in between, I go sort of like pairs of neighboring radii and take the natural logarithm of their ratio and divide by the thermal conductivity of the material in between. So when I apply that in that situation, and basically just our book assumed that this altogether is equal to UI, or the problem assumed that this altogether is equal to UI times the difference in the temperature. So I'm using that definition. It differs with the book in this 2PL term. So basically I will have 2PL RI divided by this. And if I actually plug in the numbers, I can get a solution. Now, if we eliminate the scum, so this is this layer here, okay, and I assume the same transfer coefficient between them, then basically what I'm eliminating is I'm eliminating one of these layers in the sum. So this is here in red. And also what's changing slightly now is that I have RT here on the other, because basically I don't have this outer radius anymore. So I'm using that as RT now. So that was outlined in red. So that those are the changes, and when I plug that in, I get that basically my efficiency increases only by 2.7%. Now, if my everything is the same, but my heat transfer coefficient changes to 500 from 50, then what I'm changing here is this H0. And when I do that, I get 8.4% higher efficiency. So it's better to go with actually turbulent flow, okay, in this particular situation. Okay. So that's basically two scenarios using the formulas that we were comfortable with from the homework. Okay. The last problem was an interesting one, and I'm actually going to then, I'm just going to use the picture here, but then I'm going to start writing. So I did not ask you to solve the equation. So the equation we get is pretty complex, but I just wanted you to basically put it together. That was the exercise here from the shell balances. So it says crude oil with the temperature independent physical properties, meaning that we can use the same viscosity all the time, is in fully developed laminar flow between two flat surfaces placed 2b apart. And this is the problem that we already solved in our momentum, and I provided you with the place so that you don't spend time searching in BSL where to find the solution. That solution looks like this VZ of x is minus b squared over 2 mu delta p over L, 1 minus x squared over b squared. Delta p is my generalized pressure. So it's a combination. In this case, my z is in the direction of gravity. So there is both thermodynamic and the gravity part in the term. Okay, so that's all bundled up in this delta p. Excellent. Now for z less than 0, the fluid is uniform at T is equal to T1. The temperature is uniform. So here, basically, I have a uniformed temperature. And above that, for Z is equal to 0, oh, this is actually given as a 0. So basically here, I have heating elements, okay? And those heating elements, okay, add flux going into the formula. And basically, this is where we are going to be solving. This all here is assumed constant, so there's not much to solve below here. So basically, this is my boundary at z is equal to 0, then I'm going to look into that. And it is assumed that the heat conduction in the flow direction is negligible compared to the energy convection, and that viscous heating is negligible. Okay. So state the assumptions and boundary conditions for solving this problem. This is the flow convection, or the flow velocity part is assumed solved already, and it's assumed not to change based on the temperature differences. So we basically take this solution from momentum, from the isothermal. This is an isothermal solution in 2B3 that we had before. So I'm just going to walk through the assumptions without writing those. So temperature has, so the velocity is given, and essentially I have a velocity distribution. Okay? It really depends only on x, how far I am from the wall. In z direction, I'm assuming the same profile as I go up. So essentially my VZ of XZ is the same as VZ of X. So I only have dependence on X and I don't have dependence on Z. As far as boundary conditions go, those are already incorporated in this solution and I have no slip on these boundaries. X is equal to minus B and X is equal to plus B. So that is my, let me actually write that down. So that is actually my assumption for the velocity field. VZ of XZ is VZ of X. So I don't have dependence on Z direction. No slip. VC's already incorporated in solution. Okay, now what about the temperature? The temperature boundary conditions are interesting. So one thing that we know is that we are keeping at Z is equal to 0. So XZ equal to 0 is equal to T1. And so is for everything below this Z. And then I have those heating elements that start heating the flow. Now, what do I know about the heating elements? They're adding constant flux to the system. So I have flow that is going in. This is mine. Okay. So I have flow that looks something like this. Okay. And I'm also adding flux at the constant rate. Now this direction is X direction. And flow is essentially flowing in Z direction. So since I'm keeping a constant here, but then I have sort of like uneven work of this velocity field, so it's going faster in the middle than it is near the boundaries, but then near the boundaries I have flow coming in. Essentially, there's no way this can be a one-dimensional temperature field, or depending only on one dimension. I have basically T of XZ is my 2D scalar field. And I cannot really simplify that much further. Which is why I'm asking you at the end not to solve the equation, because that would take a moment. All right, so I have one boundary condition for temperature. So flux boundary condition says that on this wall, X is equal to minus B. So that's this one. That is my X. My Q X direction flux is Q0. Okay. X direction flux is Qs of minus for any Z that is above 0 here where I'm looking. Z is equal to 0. Okay. So it's equal to a constant Q0 for every Z larger than or equal to 0. And on the other side, that's here, and I'm not certain that anybody got this right. Maybe one person did. It's a small detail, but Qx of BZ equal to minus Q0. So to enter here, if you see this, it's basically opposite what we are taking as X direction. Oops, not Y, Z. Okay. So this is, there's a minus there because to flow into the domain, I have to be negative. Okay. Now, what is my Qx if my flux is per Fourier's law? That's my Qx minus K gradient of temperature. So it's equal to minus K dt dx and minus K dt dy. Dt dz. I'm automatically going in xy because it's 2 dimensions. Okay, so this is my qx and this is my qz. All right, now it's time for, so these are the assumptions and boundary conditions. Now it's time for shell balance to derive the equation. So what is my shell? My shell is in Cartesian coordinate system. So I'm going from x to x plus delta x, z plus delta z, and into y direction. I didn't do it in 3D. There's some width w that I'm just keeping there for the proper accounting of the areas, and I'm assuming that's a constant width, and whatever I see in x and z kind of repeats in y direction, so I'm not solving for y direction. So my combined energy flux is EX EZ. I will also note that this is in, the flow itself is in Z direction, so we do have action of gravity in the picture. And that's my external force. So my external force, my Z points upwards. Therefore, my external force is given as, I don't have anything in X direction. It's minus gravity, where G is a gravity constant. And that's because Z is pointing upwards, not downwards. So my shell balance now is essentially in minus out. This is in both X and Z directions. Plus any sources or sinks for heat, which I have none. So this is 0. And then I have work of external forces. And I have 1, I have gravity. Work of external force. That has to be equal to 0, which is my steady state. So I have formally class is over. Is it okay if I just continue into office hours and solve this problem? Is everybody okay with that? If you're not okay and you have to go, this will be recorded, and I think I owe you 2 videos. So I'm gonna post them all today. Okay, so I'm just gonna continue and finish, wrap up this derivation. So this is equal to 0 steady state. All right, so what is for my X direction? I have here X, EX. Okay, so this is my in and out in X direction. So the area here, it's W of the width here, and this one is delta Z, okay? So what I'm collecting on the inside is EX evaluated at X times the area, and what's going out on the other end is this delta Z times W, that's my area, times EX evaluated at X plus delta X. So what that looks like is then W delta Z EX at X minus EX at X plus delta X, okay? Plus, now what do we have in Z direction? We do have to account for Z direction too. And this is a 2-dimensional problem. So in Z direction, I have essentially Z, okay? So I have below delta X, and then again times W, so that's my area. And what comes in is easy evaluated at Z. Minus, on the upper portion, what's coming out is that same area times easy evaluated at Z plus delta Z. Okay. And then outside forces, it's basically this work. Let me use the third column. This one. Okay. So this is rho G dot V, velocity. And now velocity doesn't have X component, it has only VZ component. Okay, so I forgot to write that down. That was the assumption from solving a momentum problem. And my rho G, well, this is the rho times this is my rho G. So what I get here is minus rho G times VZ and times volume. And volume is delta X delta Z W. And all of that has to equal to 0. So this is the main part of putting things together. And now I do standard thing, divide by volume, and then take the limit as delta X and delta Y go to 0. So divide by volume. And when I do that, I will get that minus dEx dx minus dEz minus rho GVZ is equal to 0. And you can take that as a plus, 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 if you'd like. Though terms are negative, so it doesn't really matter how you take it. And this is my main equation. You will recognize divergence in this 2D problem. This is the negative or now positive divergence of E, vector E, and then action of the external force. Now, what is EX? What is EZ? That's what I need to figure out here. My EX is 1/2 rho V squared plus rho H, I'm taking enthalpy form of it, times Vx plus tau dot V x coordinate plus Qx. So this is work of the shear forces. And essentially, what I'm going to have is that this is equal to 0. So this entire term will be 0. Okay. This portion here is when I look at the cover of BSL, it actually has a formula for this. So this is tau xx Vx plus tau xy Vy plus tau x z Vz. And these two terms are 0 because Vx and Vy are 0. And what survives is tau x z Vz, which is minus mu dVz dx Vz. Now note that there's nothing, everything here I know. I know what Vz is, so I can take a derivative with respect to x. So I know all of this. So my Ex is then minus mu dVz dx Vz minus plus Qx, and Qx by definition is kt dx. So that is my term here. Now the second one is dEz. So that's going to be used in this taking derivative of that. So I'm just outlining it so I can find it easier later. So now let's look at the EZ. EZ is equivalent to just the direction. plus tau dot v, z direction, plus qz. Okay. Now, vz is not 0. Okay. We will be taking derivatives of this with respect to z. So a lot of the terms in here will disappear because of that. But for now, I'm not taking anything at the zero as a 0. Let's look at what this is. Tau zx. By formula on the cover of BSL, there's a z component of tau dot v plus tau zy vy plus tau zz vz. And this is equal to 0 because first Vx is 0, Vy is 0. Vz is not 0, but this is taking a derivative with respect to z of Vz. And that is a 0 because Vz does not depend on 0. So this is 0 as well because Vz is Vz of x. So this term disappears and Qz is it's minus k dt dz. So what I have here left is rho vz square plus rho h vz minus k dt dz. Okay, so I'm going to take that in green. Okay, so here it is. Okay, okay. Now it's time to take derivatives. So I'm going to take x derivative of this blue term first, because that's what's in the, I'm going to call this equation 1. Why is it red now? So my 1 says, okay, taking x derivative of the first term, I have to, this is taking x derivative of a sum of the two functions that depend on x. So I'm going to get minus mu dv dx squared minus mu dv dx, and then now I take the derivative of bz with respect to x, so I'm going to get 2 of those. Minus k, taking derivative with respect to x, I'm going to get the second order derivative. Okay. Is everybody still breathing? So this is essentially what I get for my blue part. Now I'm going to continue plus dez dz. So again, I have two functions multiplied together. So I'm going to take, if I take the first derivative of the first one, I have to now figure out, well, I'm just going to write it down for now as d dz of 1/2 rho vz squared plus rho h. That's with respect to z times vz plus 1/2 rho vz squared plus rho h dvz dz. Good news is this is 0. And then minus k d squared t dz squared and plus rho gvz is equal to 0. So this is my green term. So now I kind of have to figure out what's happening in this one. And unfortunately, I gotta go to the next slide, and I didn't account for enough slides. I need to add a slide, just a moment.
I had a question.
Go ahead.
So when you have ez there, and then you do the derivative in respect to z, yeah, why wouldn't vz also be in that wouldn't you need to take the partial derivative of that VZ as well on that first term?
Yes, that's
or-
what I did here. So I
Oh,
have
wait.
this times this.
Well, you did, sorry, the product rule.
So
Oh,
yes,
okay.
product of two functions.
Yeah.
So basically I took the derivative of the first one times the second one plus the first one times derivative of the second one. And it's here that this disappears because so this entire term is gone.
So the first term is not actually a constant, that first parentheses term. So it's actually
Not all of
function
it.
of-
So this part will disappear
Mhm.
because I have derivative with respect to z over this portion. Rho is a constant, vz is a vz of x. And did everybody, I slid this under the carpet. So v square is the same as vz square because vz is the only coordinate of velocity that is non-zero. But this v square here is in Cartesian coordinates, vx squared plus vy squared plus vz squared. It's an absolute value. Yes? So I kind of just slid this under the carpet that this is immediately vz, by the way. So is everybody comfortable? So this is going to be, well, I don't know that this is ever super comfortable, but is everybody okay with it? My personal joke is that when you teach this twice, then you become comfortable. But before that, it's a little rough, which is why we have open book. So essentially, this term, derivative of this term is a 0 because my VZ does not depend on Z. But it's in this term, I do have a whole lot of constants, but not everything is a constant. Pressure is not a constant and temperature is not a constant. So I will have terms that actually survive this derivative, and that's multiplied with VZ. Any other questions before I add a slide? There. Okay, so I talked about it. Now let's do it. We need the term for enthalpy, and I gave you that in class. It's also at the end of chapter 9 in BSL. So my you can talk about so you can talk about the exam like after I finish. I'll stay online, but we can also arrange. Well, there's office hours on Friday as well, so we can definitely. So there is questions in the chat, so we can definitely talk about this after I finish. Oh, so H minus H is CP plus 1 over rho minus P0, where my H0, T0, and P0, those are constants. And their reference state, enthalpy, pressure, and temperature. And my CP is a constant as well. If I'm multiplying this by rho, the constant disappears. So this portion disappears, this portion disappears, this portion disappears. What I have left is rho CP dt plus this is only P, and when I take the derivative of the pressure, it's dP dz. So now I plug that into the first equation. And what I'm gonna get, so this was sort of a help. Oh, wow. Okay. So what I get here, well, the first part of this remains pretty much the same. It's the second part where I was plugging in what enthalpy is that changes. So I'm going to get minus mu square v minus mu dz dx squared. This is from the dx dx term, and then now I plug in this new knowledge about the enthalpy. So I have rho Cp dt dz times Vz plus dp dz times Vz, and then minus k d squared t dz squared plus rho g Vz is equal to 0. Now I'm going to combine the terms. And really, if I expected you to come to this part, the rest is now a little bit of more algebra. So there's Vz term, there's Vz term, there's Vz term, and there's Vz term here. Okay. And it's the combination, so there's Vz times minus mu. And then there's, so I know what Vz of x is. And if I plug in to what it is, it's 1 over mu delta generalized pressure over L, which is the same as essentially d generalized pressure dz. Okay? So this is plugging in the knowledge from the formula of this. Oops. Change the color back. And then plus rho Cp dt dz and plus dp dz plus rho g. And that's equal to, I'm going to put all of the other terms on the other side. K dx squared plus k d squared t dz squared plus mu dvz dx squared. Okay. This takes a little bit of recognizing or actually working through the problem that I suggested to work through from the book. So if you take this portion and this portion, mu and mu, so this is basically negative d generalized pressure dz, and this is essentially dp dz. So they cancel. And what's left is rho Cp bz of x dt dz. This, whatever it is, it's known, it's a function of x, is equal to k d squared dx squared plus these two other terms. This is a correct equation. If we take the text from the book and say viscous heating is negligible, this is approximately 0. And also conduction of heat in z direction is negligible compared to the x direction. So this term compared to this term is way lower than basically, well, this is approximately 0. So this would be the equation after neglecting terms. small terms. And this is also actually called a heat equation, where you have a double derivative of one direction and a single derivative for the same field of the other. And these are essentially somewhat constant. It's a variant of the heat equation. I do have a function here, a function of x. If one replaces this with the average velocity, then I can solve this simplified equation simpler. But I think there's an analytical solution for this, but it takes a moment to derive. So this is basically the final equation. Questions?
What was the average for this exam?
That's a great question. I will calculate it and I'll post it after the class. I think the top score, well, I'm not gonna speak from memory. My memory when I finish things at 2 a.m. is not good.
Oh,
So sorry.
okay, thank you.
Yeah, I think I said I'm gonna post that right after this. I'm gonna look at the scores. I looked at it, I didn't write it down, and I don't want to now speak from memory.
Were they bad? Or were they low? Were they low if from memory or relatively?
No, maximum was, okay, I think around 50. And the minimum, there was no, all of the scores were above 35, I believe. But again, like I'll write it down.
Gotcha. Okay.
So the
That
back.
said, there are 2 students who didn't take the exam, and I've emailed them and I've been trying to get in contact with them, but I don't know.
So the max was like 85 at most.
Yeah.
Are you gonna like curve the class or?
Yeah, don't worry.
Okay.
I don't curve per se. This is a small class, so statistics is off. But I mean, this last part was a little challenging, and I just wanted, given that you had the book, and I just wanted to see whether you can. There's certain portions like this, canceling this term, I did not necessarily expect to see, but if you arrived here with all of the terms thrown in, this is kind of what I expected to get to. So I didn't expect 100% really. And so in that sense, I'm happy with the result, if that makes you.
Why can't you say, what's it called? The temperature is only dependent in the x direction. Because that's what I did, I think. Instead
Because
of saying
the
in
flow is taking things away constantly.
No, yeah, but
flow
after the
flow is messing things up, and flow
no, but
is
like
in the direction.
I think maybe I misinterpreted it. They had a similar problem where they had like a tube and then they had like a thing that was heating the tube and the flow, but like in the tube.
Even
And
in that problem, so that problem is the same thing. You had R direction and Z direction.
Mhm.
So yes, this is similar to that problem, just in Cartesian coordinate system.
Okay.
It's
Gotcha.
essentially equivalent problem just for parallel plates, not for a cylinder. So it does have similarities with the problem that I assigned. Take a look at your own. And if you remember, I said like up until you arrived at the equation, disregard solving it.
Gotcha.
So
Okay.
that's what I basically repeated here. Now, did the class, a lot of people in the class ignore me when I said, look at that problem? That's pretty likely. And it is, but that's the 10.8 in detail, I believe. The chapter 10.8. So it has heating from the outside of the cylinder, right? So everything is similar except that you have now R direction and your flow is flow through a cylinder. So you have velocity given. It's a function of R. Vz is Vz of R. and QR on the boundary, uppercase R, is minus Q0 or whatever was the given as a constant. Does that ring a bell?
Yeah.
Yeah. So this is, again, this is the equivalent of that, just in Cartesian coordinate system.
So also, okay, so the enthalpy changes depending in the
Enthalpy has temperature and pressure in there.
oh, okay. Yeah.
That's
So
the
I can't
twist
just
of enthalpy. So you can't just say, oh, it's constant. You're
okay.
solving
Yeah.
for changing temperature.
Yeah,
In the
okay. Yeah,
world,
that makes sense.
in the world of momentum transfer, we ignore all of those changes, right? Say temperature is constant, and we're just looking at the pressure differences, and whatever is happening is driven by the pressure difference. So that's the isothermal world. In heat transport, we're saying, well, it's not isothermal anymore. I'm still keeping certain things constant. So I'm saying my fluid properties are remaining the same. And by fluid properties, I mean Cp, hat, rho, they, mu, they're constant for the range of temperatures that we're looked at. Now, frankly, truthfully, in petroleum engineering, this is never the case. Not only that I have temperature, high temperature changes, I have phase changes while doing so. And when you have phase changes, basically your basic problem, even in this, not just in the porous medium, but even in the pipes, let's say that you're in an offshore application. Basic problem is knowing how many phases do you have. So you need to do quick flash calculations in thermodynamics to figure out, oh, I have the phase. And then often what you have is like, you also have to know how is your pipe, if you're actually piping oil out of the subsurface operation, you have to, not only that, you have to kind of figure out, oh, is my, how is this oriented with the gravity? Do I have one heavy fluid on the bottom, like water falling down or oil falling down? Do I have water, oil, and gas, all three? What's happening if I have temperature changes? Then I might have separation of gas from oil. I might have all kinds of fun stuff like hydrate formation and asphalt thin deposition that is reducing the radius of my pipe. I mean, there's a lot going on actually, even though you're just flowing in pipe. Yeah. So this is what we're solving for, is simplified, and analytical solutions are available in simplified cases. And really what you do in practice, you kind of put them together. You evaluate your thermodynamics, figure out how many phases you have, and then you apply simplified solutions accordingly. And this is kind of relevant because yes, there are a lot of times we need to heat whatever it is that is flowing, or at least insulate. And when that's not possible, and sometimes in offshore operations, that's a problem. If you have 10 miles, 20 miles of pipe going on the floor of on the bottom of the ocean, it might be impractical to insulate that pipe. And if it is, then you have actually very high heat fluxes because the surrounding water is way cooler than the oil that is going within. Yeah? Yes, no, maybe? All right. Okay. Well, I'm gonna stay online if somebody wants to discuss their particular grade, or if you need time to digest it all. You have time to discuss the grading until next Wednesday. Wait, it didn't record this? Oh, wow. I hope, oh yeah, it did. It is recording. All right.
Hi.
Hello.
Um,
So are you, if you're discussing grade, are you okay with everybody else? Or I'm not sure how to organize this so that people have privacy.
yeah, I just have kind of a general question. Do you know what's gonna be the cutoff yet for passing?
No, so I'm gonna process this again. I just finished grading last night and posted everything because of my little technical trouble. I didn't have time to analyze. So I'm gonna do that by the end of tonight, probably.
Okay, thank you.
Okay. Sorry you keep asking and I keep not delivering.
It's all right.
And Hyuk, did you have questions about your exam or? Hello? Hello? Do you hear me?
For